To finish up our discussion of spectrophotometry and fundamentals of spectrophotometry, for this last half of the chapter, we're going to be looking at emission of light instead of absorption of light. So we've covered absorption, UV-vis spectroscopy, sort of the basics of a spectrophotometer. But another common way, though less common than absorption spectroscopy, to measure species concentrations is via the emission of light from chemical species. And to understand the different ways this is done, we need to understand the different things that can happen when light is absorbed and where that energy can go from the molecule. Because usually to create emission of light, we have to first have a molecule absorb light. All right, so we're going to look at a specific example. We're going to look at formaldehyde. All right, so this molecule right here. All right, so we're going to be looking at what happens when we excite one of its electrons. Okay, so we can look at if you look at figure 18-13 in your textbook, you can look at the specific molecular orbitals that are present. So this is where the electrons can be in the molecule. And what happens is that we're going to have a photon that comes in and excites an electron from one of the lower energy orbitals to a higher energy orbital. And so we can label these orbitals, we call this an N to a pi star transition. But basically, the idea is that we have absorption of light happening here. Right, so this is what we call the N orbital, meaning a non-bonding orbital, going up to a pi star orbital, which is a symmetry designation. This is an anti-bonding orbital. But anyway, we have an electron that gets excited to this excited energy level. Now, there are two possibilities here because of electron spin, right? Remember, we can have spin up or spin down electrons. There are two different possibilities for what we can end up with at the end. Okay, so we call the initial state we start in, where we have two paired electrons in this N orbital, and we have our pi star orbital up here, and there's no electrons there. We call this the S0 state. S meaning singlet, meaning the electrons are paired, and the 0 just indicating that this is a ground state. Now when the photon comes in and we get absorption, we're going to get one of these electrons is going to move up to the pi star. And there's two different possibilities here. So we can have our remaining electron and our excited electron can be opposite spins. But they're still paired with each other, so they're still different. We call this the S1 state. So this is still a singlet state, but now is the excited singlet state. And this has a specific wavelength that's associated with it for the energy required. This happens at 355 nanometers. But we can also have, we can start with this same S0 state, right, where we have our two electrons in the N, the non-bonding orbital, and we can absorb light at a lower frequency, longer wavelength at 397 nanometers, and we can have both of these electrons in the same direction. And this is what's known as a triplet state. T1 just meaning that the electrons are pointed in the same direction. The spins are in the same direction. So these could both be up, both be down. It doesn't really matter as long as they're the same. Not triplet. A triplet state. And the 1 again meaning that this is an excited state. So these two different possibilities exist. These are both ultraviolet, or I should say the 355 nanometers, this is an ultraviolet wavelength, whereas here we're on the edge of the visible spectrum at 397 nanometers. And so either of these is possible, but quantum mechanics shows us that this transition with the S0 to S1 transition is much, much more likely. So this is a highly probable transition according to quantum mechanics. We won't get into the details of why. Whereas the S0 to T1 transition is very unlikely. I ended up with an extra L there. So this is very unlikely, and in quantum mechanics we would call this a forbidden transition. I put forbidden in quotes because it still happens. Like, you can still observe this transition. It's just a much, much smaller peak, meaning it doesn't happen nearly as commonly as the S0 to S1 transition. Okay, and so in terms of if we wanted to use absorption spectroscopy, which is not what we're talking about, we would want to use this S0 to S1 transition for absorption. This is going to be a much stronger peak and give us a much higher signal. Now, what happens after this? After this light is absorbed in this S0 to S1 transition. In the next video, we'll look at what's called a Jablonski diagram to look at the different ways that our that energy can be lost by the molecule to go back down to the ground state.